a little theoretical. We're going to talk about black body radiation and some applications of that into the overall world of astrophysics. So I'm going to have a look at this and see if we can proceed, if we can go through. There'll be a couple of questions for you, so there will be some material for you to answer. And of course, we're going to take questions as quickly as I can. So nothing coming through, good. You can see in the picture that I put up for you that this shows us quite clearly a picture of the sky. Any of you look out last night after the wind had blown the clouds away at around 12 o'clock last night? It was actually, in my part of the world, a clear sky. So we did manage to see, there was some snow came about 11, but a nice clear sky, even helped by a power cut. So there was a power cut in the village, which meant the whole village went dark. And the sky was actually pretty interesting to see. Couldn't quite see the Milky Way. Okay, windows were being blocked. You mean blocked with snow or frozen too? It was not very nice. When I came back last night, was soaked to the skin, freezing cold, and it was very, very nasty weather. But the snow and ice seems to have subsided, and as I look out today, it's almost back to normal. No wind, just a little scattering of snow. Now I'm going to continue through the lesson today to show you some of those things that you could have seen ideally had you been able to see the sky. And the first thing I talked about when we went through yesterday's lesson was to discuss a little about starlight. And the final thing that I mentioned on here, the power output of the stars that I talked to you about yesterday, where we determined that the sun is actually emitting radiation. The sun is emitting radiation at different wavelengths, but the primary wavelength that we see the sun emitting light at is in the yellow area. And it's an interesting discussion because the power variation that we see of all objects, celestial objects, even planets, so planets like Venus, Jupiter, Saturn, are what we call black body radiators. The sun itself is a black body radiator, which sort of seems a little out of character and doesn't really fit into how we imagine these things called black bodies should behave. Now, my original presentation, and I think it's the one that you have in the classroom, doesn't contain these slides. I put them in yesterday because I realized that you probably didn't cover or didn't talk about black bodies during your heat discussions last year. Have any of you come across the term black body in physics lessons? I didn't mean necessarily outside. Have you come across this as a terminology that's been used at all? You just send me a yes, no, otherwise.
No.
Sorry, Charlie, the sound was turned down a little. That's better. Turn it up a little. No, that is sort of what I thought, and therefore I've added these slides into this presentation Now, as I only completed them late last night, I will change the presentation, so there'll be one or two slight differences to the presentation that you've already got, but I will put this one in the classroom, so you'll be able to see the slides that follow on from here. So let's have a look. Well, let me start off by saying that the perfect black body is a body that absorbs all wavelengths of light. No light is reflected, and we have to say wavelengths of light, and we can encompass in that all types of radiation. So no light is reflected from this object at low temperatures. It therefore appears extremely black, and we call this a perfect black body. Interestingly, perfect black bodies exist by heating objects. And not only do these objects emit radiation, but they also absorb radiation. So they absorb visible light, infrared light, ultraviolet light, and so on. And they radiate this light also at similar intensities to that which they have absorbed it. Now, that in itself is not too, I won't say difficult, not too difficult to explain, because what you can see on the right side, oh no, wrong cursor, it's this one. So if I use the laser pointer, if you look on this diagram over here, and we're going to see this diagram a couple of times, you'll see that this is made up of a number of curves, and each one of these curves has a peak at a different temperature. And as you can see, as the intensity here corresponds to temperature. So as the temperature or the intensity is higher, as we've got at this point just here, this is typically something absorbed for the sun. But if we look further and further and further down these curves, you'll see that the temperature peaks rise at different points. So we have here a peak temperature of around 6,000 Kelvin. This changes as the intensity increases. At 3,000 Kelvin, we have a maximum temperature, as you can see just here, at around 3,000 Kelvin. That's in the infrared region. So what that's going to tell us is that if we look at stars in the sky based on what I told you yesterday, their intensity of radiation is going to be a measure of how hot those particular stars are. So if we find stars that, for example, are emitting their peak radiation not in the visible part of the spectrum, but in the infrared part of the spectrum, then we will see that these stars are burning much, much cooler than the stars that are burning over here. Now, there is, of course, an area that goes beyond this. There are stars that burn much, much hotter. These will move further and further over here into the ultraviolet environment. So we get then very hot stars that are burning in the ultraviolet, very cool, or say relative, 3,000 terms of star formation, it's a relatively cold temperature. So as you can see, the intensity moves down. I'm sorry, I'm using the wrong pointer again. The intensity moves down here as the temperature decreases. So when we get out here, where we'll be looking at radio wavelengths, we can be looking at very, very low energy objects. In other words, stars that are just forming. So we can start to see a whole spectrum of different types of stars based on the radiation that they are emitting. Oops, what have I done? Oh, close my presentation. Are we back again? Yes. So now what I can do is say, right, if as far as I am concerned, this radiation is produced by all objects that are burning are going to produce something that's going to allow us to see light from that object, whether it's radio waves, whether it's light waves, ultraviolet, infrared, and so on. So what exactly is a black body radiator? Well, a black body radiator itself is any object that is a perfect emitter and perfect absorber of radiation. So onto a black body, we have, of course, incident radiation, as you can see in the top diagram here. Let me find my laser pointer again. In here, we have black body radiation being absorbed into this object. And if we place a little hole in this object, and what I would do in the classroom is we actually have an object called Leslie's cube, and that contains different surfaces. And it's a cube, 6 sides. One side is black, one side is shiny white, one side is shiny black, one is matte black, and so on. And what we can do is we can fill that object with hot water. And if we fill the black body radiator with hot water, we will get heat emitted from that object in different intensities. So why do we wear white clothing, for example, during the summer? Why is it not a good idea to wear black clothes during the summer? I know goths do, and there are other fashion statements, but as a general rule, why do we prefer white clothing in the summer as opposed to black clothing?
Because it absorbs a lot of energy, because light is energy, right?
Yeah, it's okay.
So it becomes warm, so you get, yeah.
Right. Well, there are two things. Firstly, white clothing reflects light, black clothing absorbs, as you've said. So the lighter colors tend to reflect, the darker colors tend to absorb. So what we've done in here is if we absorb that temperature, what we can then do is emit that temperature in a slightly different form. So if we've absorbed all the radiant information into this black body, we can then emit the final radiation dependent on the temperature of this body. So we're not going to see, if I'm looking through my telescope at a star that's a perfect black body radiator, I'm not going to see the radiation that's being absorbed. That's not actually quite true, because we can in some instances, but I won't confuse you with that yet. We'll wait until we start talking about spectra. then you'll see why. But what will happen is all of this radiation will be absorbed into this object. And that absorbing of energy, just like with the clothing, causes the object to heat up. So the object heats up and emits energy based on its temperature. So whether that temperature, the final temperature, is 3,000, 4,000, 5,000 Kelvin, it will emit that radiation at that level. So the peak of the curve of emission is going to be the color that you will observe in your telescope. So you might need an ultraviolet, infrared, visible telescope to see those different types of radiation. Let's take another example a little closer to home. You've all seen this. Here we have the heating elements on a cooker. What color are they? They are glowing bright red. And what's going to happen to them if you put your hand on them? You're going to find out very quickly that those are emitting radiation. Now, we consider this a perfect black body emitter of radiation. It's taking in energy, electrical energy. The energy is being converted into heat. The heat is then emitted. In this example, probably, anybody guess which sort of region this is going to be?
Maybe the red.
Well, that's a very good observation. Specifically, which red? Think about it. It's infrared. So we're looking at the infrared radiation, and we can see this. So you could use a heat camera that is only heat sensitive to observe this because it's emitting heat radiation. And that heat radiation corresponds to a particular temperature. That temperature is very useful for helping us to heat water, cook food, and so on. So there is a perfect example of a black body radiator. Other examples are light bulbs. Of course, light bulbs emit their light in different frequencies. So as most of you know, and I know that today we tend to move towards LEDs rather than the traditional old type of bulb, but you could have soft light, you could have yellow light, you could have sodium light, and so on, all different colors of light that allowed you to see those different colors. So we've now seen in this example so far different types of black body radiation. So things now start to get a little bit more complicated. What we see here are a series of curves, and a black body is a theoretical idea. But as you can see in here, many astronomical applications consider perfect black bodies as the type of objects that we can view. And in this now, what we can see is that the wavelength of the light emitted, so we're looking here, red, orange, yellow, green, blue, indigo, violet, this sort of spectrum around the 400-500 nanometers. Here we're talking about 1,000 nanometers, but look at the temperatures. We're looking now at relatively cool objects. So their peak emission is going to occur. So the radiated power at these wavelengths for this temperature moves in this direction. Of course, what I've just shown you in the first slide was the sun has its maximum temperature somewhere around here, which is going to be at this point up here, where we're looking at 6,000 Kelvin approximately for these temperatures over here. Now, if we follow that and we can see that curve, we can see what type of radiation is being emitted from stars. And what we'll get on to during next week's lessons is to look at the life cycle. And we can see star formation takes place around this area. Relatively cool. Stars burn, stars move into what we call the main sequence when they're burning at around 6,000 Kelvin. Bigger stars burn much, much faster, but they burn much hotter. And so we are able to use this information by looking at the spectrum, by looking at the temperature that the star is emitting, and it shows us then the type of star that we are looking at. Oops. So what are some applications? Well, scientists can attempt to determine temperatures of objects by observing their black body radiation. We can calculate certain criteria about these stars, and I'm going to come on to one of those in a moment. And as I've just said to you, black bodies are theoretical, but we do know that most celestial objects, objects in the sky, do follow that behavior. Let me just correct a couple of spelling mistakes. If I can find, where's my mouse there? And observing there. Right. As you can see, it's work on the go. Have we got the presentation back? No. Did I lose it? Right, so now what we've got, if we consider any application that uses black body radiation, how do we justify that? Well, this slide looks a little complicated. What I'm going to, E lambda equals 8 pi hc over lambda to the 5th c to the hc over lambda kt, all minus 1. I'm not going to talk about that. What you will see in here, and the point of putting this slide on the screen, is to show you that there are 3 laws which are applicable to all black bodies. So astrophysicists are able to use these laws to give them indications about what they can see. And the first one is Planck's law of black body radiation, which is a formula to determine the energy density at each wavelength. And that gives us then a sort of measure of the size of a star, because we can see how much energy is being absorbed or emitted at different wavelengths. The second one is what's called Wien's displacement law, which looks at the maximum peak emission frequency with temperature. We're going to have a look at that one in a moment. And the final one is the Stefan Boltzmann law, which equates to the total energy and absolute temperature. Now, you may have mentioned Boltzmann's law last year in the heat topic that you covered. And we talk also about the distribution using Stefan Boltzmann mechanics in order to set up this standard distribution that you've seen for the temperature distribution. So it does tell us that inside a perfect body, whoops, I want to go back, where are we? This one. It does tell us here that inside a perfect black body, even though this object is emitting primarily light at 1000, 1250, 2000 Kelvin, it is still emitting light at different wavelengths. And if you remember from last year that when you talked about heat, heat is the energy absorbed by molecules. And when you look at the molecules in a gas, for example, those molecules are vibrating backwards and forwards. And each set of molecules has peak energy corresponding to one of these temperatures. So if the maximum temperature of a star is 1250, there is going to be a distribution of molecules in that star that are also going to be hotter. They're going to be much hotter, but they're balanced by other molecules that are going to be much cooler. Only what is observed here, and with the Stefan Boltzmann law, is we are looking at the peak temperature. So that allows us to see how we are doing. Okay, I'm sorry that was a little theoretical. I think it's important because black body radiation is a vital part of the setup of what we are looking at in our astrophysics world. So now we can start to look at the specifics of these. And the one law that we do need to know about, that Skolverket say is necessary for the physics and astrophysics student, is the relationship between the peak power wavelength and the temperature at the surface of a black body. Now, this is an interesting thing because I don't know whether any of you realize that the temperature on the surface of the sun, and indeed, if we can even call it a surface, because it's a molten mass of molecules at around 6,000 degrees on the surface, but the corona round the sun can actually be much hotter than the surface of the black body. And that in itself causes problems because some of the heat doesn't escape. It's absorbed by the corona, for example. And that means that we need to look at the temperatures, for example, on the surface of our black body. Now, Wien's law says the wavelength at peak power, in other words, lambda max, is inversely proportional to the absolute temperature of the surface of the black body. In other words, the wavelength times temperature should equal a constant. And this constant is known as, what we can see in here is the Wien displacement constant. It is marked as an MK which is not, in this example, does not mean millikelvin, but it's meter Kelvin, because we're dealing with a wavelength. So wavelength in meters, temperature in Kelvin. So the constant is 0.0029 meter Kelvin. And this equation can be used to determine the temperature of the surface of a star. And this is also known as the photosphere of the stars that we are looking at. Right, now, if I've talked to you so far about stars, temperatures, and colors, I think in yesterday's lesson, if I have my notes, one of the things you mentioned was that the colors of stars vary. And you're quite right. The star color, as you can see from the wavelength formula determined by Wien's law, is dependent on the temperature. So what we can do now is we can have a look at what the relationship actually works out to be. And what we can see is that as the temperatures change, we get peak increases in temperature. And what you can see on this diagram is that we can go through each of the examples of star color, how that equates to its temperature and the wavelength, and for example, an example of each of those particular stars. So the first one is a red colored star. Red colored stars tend to have their peak emissions down at this end of the spectrum. So we're looking at infrared, we're looking at low end red colors, typically temperatures of around 3,500 Kelvin. An example is Antares. Again, you can see these, you can find these stars on star charts, and you should be able to see most of these. If we move slightly further up, as you can see in here, we've started now to move in towards the visible spectrum. So orange colored stars with surface temperatures of around 4,300, 670 nanometers. You'll remember the lasers that you used a couple of weeks ago in the lab had their frequency, their wavelength of about 650 nanometers. So we're clearly now into a visible part of the spectrum. A typical example is the star Arcturus. Moving further into the spectrum, we can move into the yellow region. Notice that our temperature is moving upwards here, and we're moving further across lower and lower in wavelength, but we're increasing the output power of these particular stars. So again, yellow corresponds to a temperature of around 5,500 Kelvin, 530 nanometers, and an example is Capella. Move further up this score, we move into the white region. Now, the white colored stars are actually burning at blue temperatures.
Yeah, there we go.
Thank you. My second system switched off, so the presentation's running on another computer, which I can go back to, but white stars, we are now looking at a region where the stars are appearing to be white in color, much, much hotter, as you can see, around 7,500 Kelvin. These are actually peaking now in the blue part of the spectrum. So around 386 nanometers. And again, an example of this is Altair. Finally, we're looking now right at the top end of the ultraviolet. So these types of stars would tend not to be seen by visible telescopes. As you can see just here, this now peaks at its maximum outside of the visible range of light. So in theory, if we were looking through the Hubble Space Telescope, we probably wouldn't see this type of star. We would see some parts of it, but not the typical amounts that you would expect. Now, there is some element of visible light, but it wouldn't be as intense. And as we see here, the peak intensity now with stars burning at 20,000 Kelvin is in the ultraviolet region. So we're now starting to see stars which are in a very, very different scenario. If there are any questions, I think that I lost the questions from the previous presentation, but I can still see them. So please, any questions? Right, so let's see if we can move on. So we can summarize by saying that blue stars are hotter than red stars. So if we're looking at anything from the red to the blue end of the spectrum, it's going to give us an idea of what those particular stars are doing, what their temperatures are. So you've sat around for long enough now. Let's see if you can do a calculation, please. Calculate the peak wavelength emitted by the sun if its surface temperature is 6,000 Kelvin. So you need the formula which you have just seen. And let's see, that's why it wasn't on the previous set. I thought some of you may have asked, why didn't we put the sun on there? The reason is you can calculate now the peak wavelength, please, emitted by the sun if its temperature is 6,000 Kelvin. Very good. So we're getting some pretty good answers. Good. That's what I like to see. I'm just taking this this opportunity to do the register. Right, so I think you're pretty unanimous. Assuming the sun is a black body radiator, so remember these are like exam questions. State all the facts. Assuming the sun is a black body radiator, applying Wien's displacement law, lambda max times t equals 0.0029, which gives us then peak wavelength of 483 nanometers. So you've actually now solved one of the first questions that I've asked you. Now, that means that the questions, or what we are looking at in our examples, fit into scientific recognized laws. The second question now shows us if you can do the same thing again, we have two completely different stars. And you'll see here the constellation of Orion. I think it's fairly well known for the two shoulders, the belt, and then the two legs here. Well, we have Betelgeuse, which is the red giant up in the top corner, and Regal, which is a blue supergiant star. And we'll come on to these size classifications again a little later. But these give us now the opportunity to guess something quite interesting about these two stars. So please try to complete. Wow, quick working. Good, well done. So starting to see again. Right, so let's just see again. This time we're applying the same logic. So this time the temperatures now are giving us, for Betelgeuse, around 3,500. Let me just check. Whoops, where are we? So you've got around 3,500. Let's not worry about the two, but being pedantic, of course, that is correct. And for Regal, we get around 11,000. Question again for you. Are we looking at two stars that are in any way related to each other? Any guesses from your perspective? Are we seeing two stars here, Betelgeuse and Regal, that are in any way related? They're in the same constellation, so they move around the sky in the same way, or don't they? Any guesses? No. Okay. There are absolutely no relation between these two. They're not close together. They are at completely different distances. Oh, excuse me. Completely different distances apart. They are thank you. They are independent of each other, and their temperatures are the important thing. Now, Betelgeuse as a star, because we'll look at some other things as we see these stars progress, is a star that's coming to the end of its life. So it's burnt all of its fuel, and it's now at the end. It's in its final throes, waiting to become some catastrophic event. Rigel, on the other side, is very, very hot in terms of a star. So this star is burning brightly. It's a very intense star, very hot, and it is a relatively young star. So we've got two complete extremes here in one constellation. And those two extremes allow us to then be able to discover something about the life cycle of these stars. And the temperature is the first step in that calculation. I'll just go through this calculation for you. Again, using Wien's displacement law, we're simply looking at a displacement power here. The thermal temperature of 2.7 Kelvin corresponds to 1.1 millimeters wavelength of light. So we are looking at something which is not a major disruptor, is not going to be something of maximum power that is going to upset our books. But this is now into what we call the microwave environment. And this now tells us that the 2.7 Kelvin, which is almost 3 degrees above absolute zero, is the very large black body of the universe. So this background that we see, and we'll get on to talk about the discovery of the cosmic microwave background, but you can see here that the universe itself is a very, very, very large black body, and it is emitting a constant level of radiation. And I think one or two of you said, when we mentioned this a couple of weeks ago, talking about the white noise you used to get on TVs, for example, that was the radiation, the background remaining, not necessarily from the universe, but it's a background hiss that's permanently there. We can't hear it because we don't hear microwaves. But if we were sensitive to microwaves, we would hear that all the time. And the cosmic microwave background radiation was first discovered or detected in 1965. So this was not an early recognition. This was not something that scientists had expected. And it came about in a very, very strange manner, which I will tell you about. But the important thing there, of course, as it says here, it's one of the main pieces of evidence that does support a Big Bang theory, because there is something left over from an event that occurred. And if we trace that event back, it gives us then this origin of the universe at about 13.7 billion years ago. Now, I mentioned in the black body discussion, there was a similar law, or a third law, that allowed us to look at also the relationships that occur within stars. And this one is slightly more complex, because the total energy per second, or the power emitted by a black body at a temperature T, is proportional to its surface area and the fourth power of its temperature. So now what we've got, if we can establish the power output of a star and the temperature of that star, it now allows us to calculate something to do with the surface area or the size of these objects. So let's have a look. Power output is theta A times T to the power 4. And we are looking here at the constant known as Stefan's constant. And that constant now gives us a way of calculating in our equations the surface area or the diameter of a star. So we've now gone from having something which allows us to firstly determine what type of star we are looking at, what sort of temperature that star is burning at, but now using another master stroke of physics, we're able to determine the surface area or the diameter of these stars. So we can now start to see that these are real objects. Now, we couldn't take a protractor and measure the size of the star. That is not possible based on the distances and the sizes relative to those distances. So we have to use an indirect means, and Stefan's law allows us to do that. Now I'm just going to go through one of these questions so we can see how that will work. And I think there is a second question for you to do. So calculate the power output of the sun if its diameter is 1.39 times 10 to the 6 kilometers and its surface temperature is 5,800 Kelvin. So area of a sphere, so the surface area of our sphere, 4 pi r squared. So we now get an area of 10 to the power 18 square meters. And assuming the sun is a black body radiator, you can apply Stefan's law. So now we can look at this object and we will see the power output of the sun comes out now at 3.89 times 10 to the 26 watts. Is that in close resemblance to what we'd worked out previously? If you remember, I think it was the beginning of last lesson when we were looking at calculating the power output of the sun. I think we got a figure relatively, certainly it was 10 to the power 26. So we got something that is in pretty close agreement with what we would have calculated from other methods. So this has allowed us to calculate now power output knowing the radius. And as you saw, this is also the value that we calculated for the sun's luminosity. As I said, it agrees closely with the luminosity calculation based on 1360 watts per square meter of sunlight intensity data. So we've got now two completely different ways of stating the same thing, which sort of now gives us confidence that what we've done is correct. So if we can now go into the alternate and we know the output power and the temperature, we can work out the surface area and ultimately the radius of stars in our view. So I would like you, please, now to calculate the surface area and the radius of Betelgeuse. You see its luminosity, so 4.09 times 10 to the 31 watts, and its surface temperature, 3,500 Kelvin. Where did I put my... Right, so how are we doing? Good. We are in the ballpark. So let's see if now we can calculate. Applying Stefan's law, we'll start to see that we can calculate the surface area being 4.81. So applying your formula, and we get 6.18, 6.2 times 10 to the 11 meters. That now is sort of giving us an estimate. Is that big? Anybody, is that big? Or think about the Earth or the sun. Tiny. Think about the Earth to sun. Think about it's gigantic. Thank you. If you think that the radius of the Earth from the sun is 1 astronomical unit, 150 million kilometers. This is 4 times the size of the Earth's radius around the sun. So Betelgeuse as a planet, as a star, is 4 times in diameter the size of the Earth from the sun distance. It is massive. And this is what we call a supergiant, a super red giant. And you'll see the reason for this. I'm not going to go into that at this very moment, but this is one of the largest stars that we're going to look at. Now, having said that, and since this is, I put this presentation together a couple of years ago now, we have stars, we actually have black holes that are reputed to be bigger than these types of stars. So these things are changing, but this is useful for trying to give you some feeling for the stars that we are looking at. And hopefully this is going to start you maybe with some interest. As you can see, 4 times the radius of the Earth, 3/4 of that orbit where Jupiter is located. And that's why we call this a super giant or super red giant. Right, now, I think that I am not going to continue with this next part of the presentation. I will be in school next Thursday, so I will set up some apparatus for us to actually look and see some of the stellar spectra, some of the things that we need to look at in terms of spectrum, how we need to calculate, how we can see, and what we can determine from that of a spectra. I would just make one request of all of you. If any of you have anything like a lens or a piece of glass even that you can just use next week during the lesson, I'd like you to have that on your desk, have it available. If you've a lens, so much the better. And we'll have a look and see if we can use that to demonstrate some of the effects that I'm going to show you next week. I'll be able to show you them in the lab, but I'd like you, if at all possible, with a pen torch or even with your mobile phone and the lamp from your phone, you should be able to produce a spectrum which we can look at and talk about. Do glasses work? Yes. Your only thing may be, I'd prefer that you used a broken pair. So if you've got a pair that you can use, because you want to shine light onto these at an angle, and you know, your sort of what do you call them, supports on the side are going to get in the way. And it would help if they are actually of glass, not, yeah, if you've a broken pair, that's fine. As opposed to these are plastic, for example, that won't work. Plastic is not as good a breaker of the light as I would like. So if you can find something, another example, and a great example, if you have a broken bottle, the bottom of a bottle tends to be, if it's a white glass, tends to be sort of shaped, and it allows you, but it's just a little bit dangerous. So if you can find something, a piece of glass, a chunk of a lens or something like that would be useful. Any other questions?